Hi, everybody. I guess I get to be first today. And we only have 30 minutes, so we're going to go really super fast. Okay, so I find hundreds of bugs a year, lots of them in industrial control systems. And so most bugs are just bugs. I report them back to the vendors fix them, CVEs are usually never generated, and the cycle repeats. The problem with this system is that reporters, or that C-level executives, mostly get their news from headlines filtered through reporters. So every now and then, I have to go talk to some reporters. I've talked to some today, actually. So I was talking to a reporter about some very average bugs that I'd found, and the reporter came to two opposite conclusions. One is that these bugs could easily be used to take over industrial control systems by anybody, and that they were only usable by APT, nation-state kind of people. So that kind of tweaked me a little bit. These are completely opposite conclusions, and the only reason you'd come to those completely opposite conclusions is because it makes the best headlines. So I talked to him a little bit, and I was trying to come up with a rebuttal, and I realized that there wasn't anything I could point them to in the open literature about what an average consultant or what an average guy accomplishes in an average gig. There was no way to say, like, yeah, this is just some sort of average stuff. So what I did was I started taking detailed notes on my next gig about what I was doing hour by hour so that I could have that, send it over there, and do kind of a rebuttal to these guys. So what does an average engagement look like? What exploits do we generate? How long did it take? What techniques did we use? Those kinds of things. So this presentation is going to cover the first 14 hours of my next gig. I took notes for the whole thing, but we're only going to cover the first stage of it. So I'll cover what I was doing each hour, and then at the end, I'm going to have a point to make. So I'm going to go through all this super fast, and then hopefully I have time to make a point at the end. So the scenario was this. In a previous engagement, I'd already hacked into this particular electric power utility and gotten control of the EMS network. So in the second stage, they're getting a lot more renewables on board. And since they have lots more renewables, they have lots more zones that can sit there and island. And lots of bad things can happen when things come out of islanding because of phases and switches and all manner of other things. So most of the protections against bad things happening when things come out of islanding happen in all of the protective relays down in the substation. So my job was to hack from the EMS network down into the substation and disable all these protective things, just to see if it could be done. And these guys had a very typical network. They had an EMS network where the operators sit, and a backup EMS network, and all those types of things. Set of firewalls in between the EMS servers and their data DMZ, which is where all their field data came in there. So only the field equipment could talk to the EMS networks and not other random boxes, etc. And then they have fiber optic cable and microwave links and all the other things. So this particular utility, almost all their data back and forth to their substations and switch yards and whatnot was still serial data. So they had a bunch of serial to Ethernet converters in the middle here, which talked to a bunch of RTUs. And then down in the middle of the substations and switch yards, then they have a bunch of substation automation equipment. So this is a very, very typical scenario. So the first thing they did was came over there and dropped a bunch of these guys on my desk. And so like, here you go, cha-chunk. The first time I'd ever seen them. So these are Moxa Ethernet to serial converters. So on the back of them, you've got 16 serial ports and an Ethernet port, and you wire up each one of your field equipment serial ports into the back, and comes out Ethernet in the front. So this is hour one. Let's go hack this thing. What did I do? So first thing I did was an in-map scan, just like everybody else. We've got a whole bunch of open ports up here. These are mapped pretty much one-to-one to the serial ports in the back. So you establish a TCP session, and you get to talk to the serial port. They've got HTTP and Telnet, and then a few custom services on the back. So hit the Telnet console, and it told me the firmware revision, and this happened to be the latest firmware revision for this device, so everything's patched and up to date, and the utility is doing all the things that it should be doing. So the first thing, the easiest way into most embedded devices is through their web console, and this one just pops up and ask for a password. There's only a blank page. Once you get past that, you can adjust all the settings and things like that. But first you have this, please just type your password. So I also went out there, I pulled the firmware off their website, which was downloadable, and they had this little Windows administration utility up there. And this is what you do to do the firmware upgrades. So, so you can also modify all the COM port settings, all those things with a little utility. So I downloaded and I grabbed a copy of both of those. So the next thing I wanted to know was what OS was this thing. So I started sending a bunch of TCP things, and I looked at their sequence numbers and initial acknowledgement numbers and that type of things. And these are actually based on time, and nobody's done this since like the 1990s. Like really, really super old TCP IP stacks from way long ago may have done this. So this isn't Linux, it's not VxWorks, it's not anything. And if they wrote their own custom TCP IP stack, they probably wrote their own custom everything else. So this is probably an OS that I've never seen before and is not documented anywhere. So I pulled up Burp Suite. I looked at a bunch of the HTTP auth that was going back and forth, and it pretty much came down to this. It sends you over a challenge, you stick on the password, you take the MD5 sum of that, and you hand it back as a cookie, and that's what lets you in. So there weren't any real flaws there. There were some timing issues and stuff like that, but they're not really practical to exploit. And since my job was to actually go down and get down and do all those things, that wasn't really a good exploit. So that took the first hour or so. And this web thing really wasn't working, so I started looking for another way in. So the second thing I did was look at the firmware upgrade. So the first thing you have to do before you can upgrade the firmware is unlock it. So the unlock isn't tied to a session. Once you stick the device in the unlock state, anybody from any IP address can actually come and upgrade the firmware and do whatever they want to. But that's kind of a really lame exploit to like hang out and wait for somebody else to unlock it. So that didn't really work out. So I looked at the firmware upgrade, and the first thing it did was send a bunch of UDP packets back and forth to port 4800, which was the first one of those mystery ports we saw there. Then after that, it actually used a TCP session to the other mystery port. And I looked at the handshake going back and forth, and this looked really, really like the web authentication. It sends over a number, and we send back a number, and so I just emulated that a little bit, and yeah, that was the same MD5 challenge. So unlocking it from the TCP session is the same as unlocking it from the web session. So I looked at the firmware upgrade a little bit more, and so there's a few back and forth packets. And then this packet over here that had something that looked, that was super, super close to the number of bytes afterwards. So this is probably the length field. So a couple of handshake packets, a length field, we're all good. So I looked in the firmware update for the bytes that came over there, and the firmware update actually had sections on there. So the web server stuff up here is upgraded in a different partition on the flash than the actual firmware. So up in the top, then pretty much there's a magic number. There's a length, which is about 20 hex bytes different than the length from the actual firmware upgrade, and a 20 right here in memory. So I kind of surmised that this was a header. So we've got a 32-byte header. So I whacked off the 30-byte header, threw it into IDA, told it it was an ARM Little Endian processor, which is the most common processor, and set it to decode. So there was no symbols in this, so any names you see over here are actually my names and not the names that the programmers actually stuck on there. So I've got the firmware extracted now, and so now it's just the long, slow slog of reading the binary, so hours 3 through 5. So the first thing I did was run around, find all of the debugging messages that actually had names of functions, and I stuck all the function names there. And I looked for anything that looked like it had a TCP/IP related thing or port-related stuff in it. So that eventually led me to these things, and then with some educated guesses, I figured out where all of the BSD socket binds, all those things. So they wrote their own TCP/IP stack, but these weren't terribly hard to find. So after that, then I eventually came into this function. So this function calls receive from to grab a UDP packet off the network. I know that it's got a 2-byte length field, that it's got a 12-byte token, and the 12-byte token is mostly based on the MAC address, and there's 100 and some odd message types. So I'm still into it about hour 2 or so, and I started to read through the actual messages. And so when I got here to message 1F, then I started reading through it, and what this looks like is it's taking 4 bytes out of the packet and passing them to this DUC get mem value, which is just a wraparound mem copy. So all this does is you actually get to give it a pointer in this UDP packet, and it will read memory from the pointer. And since this is totally flat firmware, I can read from anywhere in memory. So this is probably a debugging function somewhere up in memory that they left into production firmware. So this is there for debugging. So I whipped up a quick Python script and told it to debug to drop all of memory. Actually, it can only read the bottom half or the top half of memory. I think they put that in there so people didn't accidentally read across the memory mapped I/O section, because if you read from that, you'll pop bytes off of serial ports and stuff like that and mess up the internal state. So I dumped it all, and I went looking through it, and lo and behold, here was all the settings, and here was the password for the device. So I now have a primitive where I can go hit this, pull off the password, and go take a look. So now I have an evil genius plan. So with a password, I can unlock the device, and assuming that there's no cryptographic signatures or anything like that, I can write an implant. Upload it to the RTU and get all my man in the middles and everything else that I'm going to need for this gig. So that takes me to about hour 6. So it's hour 6, and I hit the sweaty palm stage of doing one of these. So these boxes are a couple of $1,000s a piece, and if you brick them, then they're bricked. And so the problem we have with these is you need the firmware to be running to be able to upload the firmware to fix the firmware. So if you mess up the firmware upload, there's no firmware to upload the new firmware. So then you're just toast. So I whipped up a little unlock script in Python and started to do the glitchy part. So the first modification I did was I popped in there and I looked for an easy string that doesn't change the thing. So what I did was I changed this please key in your password to please key AA your password. And I'm like, okay, that's a nice human readable string. It's not going to change the execution flow. Let's just change something small, upload this thing. So I tried to upload it, and it's like, no. Yeah, you don't get to upload. So obviously there's a checksum or a signature I missed somewhere. So I went back to the header and started poking around a little bit. And so there's this nice random number right after everything else. And so I poked at it a little bit and figured out that this was actually a traditional checksum. So it's actually casting the whole chunk of the binary to an array of integers and adding up all the array of integers is actually checksum. But there's a reason that we don't do this anymore, because computers, when they freak out, a lot of times send big blocks of zeros to things. So you come whether you get a length field wrong or something like that, and it's like, here's a bunch of zeros. So the reason we don't do this anymore is because if you add up a whole bunch of zeros, the checksum is a whole bunch of zeros, which then bricks your device, because the checksum all match. So I updated the checksum with a little Python script, and success, I now have code execution, so I can upload my own firmware. So I can do all of the firmware modifications I want. So now I'm into about hour 7, and now we have to get to baby's first implant. So the first thing I need to do is build an in-memory debugger. I need to be able to write stuff into memory, read stuff out of memory, and execute code in memory so I can figure out where all this stuff is. And I want these modifications to not run at boot up because we might brick the device. I don't want to, every time I upload a new test firmware, I don't want it to be a chance to brick the device. So I want to make several very small modifications that allow me to then, at runtime, upload my new updates so I can test the updates. And then when I finally get done, I'm going to write those updates back to the master firmware file and get it done. So I need an in-memory debugger. So what I did was I went to these UDP things I'd already reverse engineered, and I added I removed the read check so I can read all of memory, and then I just hijacked one of the other functions I wasn't going to use and turned it into a write check. So here's the RNC if people like to read C better. So now I have read and write primitives, and I upload my in-memory debugger version of it, and now I can read and write from memory. So I did the same modification I did previously because I know that modification doesn't brick the box, and so I told the in-memory debugger to change the string. The string changed. I'm all good. So the next thing I need is a code cave. So I need to upload a rootkit into the middle of this, and the rootkit has to live somewhere up into the RAM. So I basically have 3 choices. I can find some unused memory that the programmers just didn't use something on the end, I can erase some stuff. Like, I don't need a web server. I can just throw the web server away. We don't need no web servers here. Or I can move stuff around to make room. So compilers are horribly inefficient. So a lot of times you can find like 17 copies of mem copy or stir copy or something in memory, and then you collapse those down into one copy, and they get to reuse all the memory that you saved. So I just went to option 1, and lo and behold, at the end of memory, there's 1.7 kilobytes of sweet memory up there. I can totally stick a rootkit into a 1.7 kilobytes of memory. I used my hijacker to create a jump pad so that I can test out my rootkit, and I started building a tool chain. So handwriting assembly is super slow. So I like to write all my implants in C. So usually I only write enough assembly to bootstrap C up there. So I got a cross compiler up, a big linker script that'll go there, and then I wrote the same modification in C, and I can upload C. So now that I've got C, I've got a whole bunch of standard utilities that I can do. So since this particular utility is using DNP across this link, I've got a whole bunch of off-the-shelf DNP man-in-the-middle link code that I've already written. I can just compile it, target it to the appropriate sections, and I'm up, and I don't have to do anything. This actually turned out to be an ARMv4 cross-compiler, so an ARMv4 architecture, so I had to hand-build another cross-compiler for it. So that brings us up to about hour 9. And about hour 9, then I start hooking the data path. So I've got DNP man-in-the-middle code, but I need to figure out where the reads and writes from the sockets and serial ports are, because I have to go hook those so that things come out there. So one of the problems that I've got is that this is a serial to Ethernet converter, not a DNP converter. So all the bytes are going to be popped off 1 or 2 at a time to throw over there. And if I'm going to do a rootkit in the middle there, I need these bytes to be assembled into DNP messages. So I have to hook these 2 chains and then take the bytes off, queue them up into memory, then figure out whether or not I'm going to modify them or add new DNP messages on the end or drop the DNP messages. I have to do this in both directions. So I whipped that up real quick. It actually took me quite a while to find the correct function. There was a whole bunch of different modes, and I had to find all the modes and hook them all up, and that was kind of a pain. So the next thing I needed was the spoofing tables. So since this utility was kind enough to let me hack into a live power grid, I don't want the manager to show up with this angry face of like, you broke my power grid. That's unpleasant. It's happened a few times. We don't want to go there. So what I want is, as I'm playing with everything down in the switch yard, I don't want the operators or any of the equipment upstream to know anything about what I'm doing. So what I want is the spoofing tables. So we're going to show the operators and all the equipment up there happy land where nothing has changed and it's all still in its same state. I'm going to work off the real world values. So I whip up some spoofing tables in the middle. We start recording point numbers. We get all the point numbers, and when everything changed, we keep saying the happy value, and then we go there. So now we're into hour 10-ish. So in hour 10, then I have to deal with the what we call the physics payload. So this so this is a test where I'm going to go down into the switch yard, and I'm going to have to test for islanding. So I need to know, is this a plant in startup stage? They had this really weird plant in this one. So it has a cogen on the side, and so when it starts up, it draws a whole bunch of electricity. And then after it draws all the electricity in startup, they actually start generating electricity and then feeding electricity back. And so it goes back and forth, and they have lots of problems with it. So I need to figure out all those states. So I have a bunch of points going back and forth, and I need to turn that into some sort of higher level mechanic. And so in the higher level mechanic that almost everybody uses that does this is some sort of truth table, where in startup, you say, these are the point values, these are what I'm comparing against, this is the comparator, and if all these go true, I can jump down here into the next stage. So the problem with truth tables is that they get really large, but you don't need the entire truth table all at the same time. So I spent an hour or so compressing the truth tables. So my mechanism is a little bit different than everybody else. I think this one's unique to me. So what I do is I actually take the truth tables, which are highly redundant. We'll have whole sections that are repeated in the middle of it. And so since they're highly redundant, I can compress them. But there's no compression routines already in there. So it doesn't make sense for me to use something like zip to make them smaller, because then I would have to upload a copy of zip, and that's going to be bigger than the truth tables. You probably can't stick a whole copy of zip in 1.7 kilobytes. That's not going to work. So actually what I do is I use a set of linear feedback shift registers. And there's an algorithm called Berlekamp-Massey. And in Berlekamp-Massey, then they'll find you the minimum LFSR. And then you can actually take the seed for each one of these states, read it to the LFSR, clock out your truth tables, and then they're nicely compressed, and you have the chunk of the truth table that you want. Oh, yep, and LFSRs and Berlekamp-Massey. I guess I should advance my things. So that takes us all the way out to hour 14. So I found the device, I've uploaded the device, I've stuck an implant in there that will stop the operators and everybody else from seeing all the stuff that I'm down there, and now I'm ready to deploy it. So pretty much my deployment strategy was I'd already compromised the patch management system, which was one of the things privileged to talk into the DMZ. So I threw up my my new firmware implant. I threw up a little Python script to install it, and we call this one done. So over the 3 weeks of the engagement, then I wrote exploits for the USB to serial converters, the RTU. This one, there were a bunch of trivial buffer overflows I took over there. Then I had to get the switch yard had two halves. It had the control half and the safety half. In order to disable all the stuff I was supposed to, I had to get across to the safety half. And how I did that is they actually had an IDS plugged in down there. And so I found and wrote an exploit for the IDS, took over the IDS, got across the half. Yes, IDSs are expensive. You know, you can only have one for both halves, right? Took over the other half and took over some embedded systems down here, and I got down there. So the whole chain took about 3 weeks to get done. But all of these bugs have been reported to the vendors. All the bugs have fixes out that you can go download, but no CVs have been generated or issued at all. And that's kind of normal in these things. We normally just don't do that. So after 14 hours, I said I had a point. And here's the point, is I think there's too much James Bond creeping into the analysis of all hacking, but especially ICS hacking. So the reason I did this one is mostly to grumble at people doing James Bond analysis. But this particular serial converter is rumored to be the same one that were used in the 2015 Ukrainian attacks. And so I wanted to compare the level of effort to something that somebody had talked about a lot, so we could actually have a real discussion on how advanced these guys were. So let's talk about this cast of characters. So the first one is what everybody talks about, this unknown state-sponsored, well-funded hacking group. So they're professional, goal-oriented. As an ATP, then they're generally locked into their ways. That's how we classify them, because whenever they need an exploit, they need to look like the other exploits because it fits into their process, because they've got a whole bunch of people. Before you grumble at me, in this case, I totally think this is the correct analysis. Let's go all the way to the other end. I have a whole bunch of friends in Seattle, and they used to be computer security consultants, but now there's legal weed there, and they spend most of their time smoking on bongs and reading social media hate mail. You know, social media rage culture is really big. But these guys are totally capable of doing this level of work. Everybody that I work with is totally capable of doing this level of work. So these guys aren't terribly motivated because mostly they live on bug bounties. You know, it's like, oh, we're running out of pot. Okay, find a bug. Here's 20 grand. Okay, more pot. You know, it's a lifestyle. Not my lifestyle, but you know, it works. In the middle, we have professionals. So when professionals are totally capable of doing this, the professionals generally are only there for a short period of time. In my case, 3 weeks. There's good guy and bad guy professionals, but there's lots of professionals in the world, and we've done ICS hacking for long enough that there's guys that just make their living doing this. So do whatever's fastest, time is money. And all these guys are perfectly capable of reverse engineering a chunk of firmware and writing an implant. So this level of implant is terribly not out of the realm of a whole cast of characters. So if my pot-smoking buddy said, like, oh, yeah, there was, this Ukrainian thing, and we got really mad, and, we wrote some exploits, I would totally believe them. I'm sure that there's some Russian or unknown pot smokers out there that could do this. Totally a bunch of professionals can do this, and totally a nation state has done this. So my grumble is that we tend to keep jumping to the head and saying, like, these guys are all super powerful, all-knowing things. And the super powerful, all-knowing thing, it's not really backed up. This was a very average engagement for me. I do this day in, day out. This is what I do for a living. And lots of other people do this for a living, too. And so we're giving these APT guys way too much credit, and we're getting some inflation in the actors. So there's a lot of these things where they're saying, like, oh, this is obviously new ATP, and I'm like, oh, no, it could be some college kids. So I think we're getting actor inflation across a bunch of these. Powerful people can do these things, but they don't have to be powerful people, and the techniques they're using and the exploits they're generating don't lead me to believe that they're totally unstoppable, or even that they would take more effort to stop these people than it would take to stop, my bong-smoking buddies on some sort of, social media rage. And so that was kind of my grumble at the end, and I wanted to come over there and say, like, okay, so I think the thing that I wrote for the converter was way more complex, and I did more in the middle of it, and it only took me 14 hours. So we shouldn't give these guys way more credit than the 14 hours it took me. So maybe it took them 40 hours or 60 hours. This is still not a huge investment of time for any one of these actors. And we shouldn't come over there. So one of the reasons I think that we're getting the inflation is because it's easier to talk to your boss about things. Like when you come over there and say, like, hey, I need some more budget, it's really easy to say, like, there are these nation-statey big guys that are coming for me. I need big budget, rather than bong-smoking ex-security consultants. I think that sells better. And when you get compromised, I think this also sells better too. Oh, who took you over? Well, yeah, some nation-statey ATP guys, right? Totally not the bong smokers. So that was kind of my grumble, and I wanted to kind of get down to these are very doable things. They don't take a lot of effort, and people other than APT guys can whip them up. And so, as the parting comment on to the last on my thing is, the cross-compiler that I originally got, I actually got from one of my bong-smoking buddies, and it had a command line option. And I'm like, what are these extra command line options you stuck on there? And he's like, oh, well, so we tore apart a whole bunch of APT malware, and we stuck in binary blobs from them all over there. And so when you compile, it'll sprinkle the APT binary blobs across it and stick some strings in there from these guys in the middle of it. I'm like, why are you doing this? They're like, well, because the analysts, as soon as it says it's part of this APT group, they stop looking, and nobody ever comes after us. So this analysis has gotten so bad that just random guys are actually taking advantage of this to basically make it hard for them to come over there, because nobody's going to come after one of these APT guys because they're big evil nation state people and are too hard to track down. So anyway, that is my my presentation and my grumble. And so, are there any questions in the 2 minutes or so that I have left?
When you were talking about maybe hour 2 or 3, I can't remember, when you were checking that they had traditional checksum on the specific device. What is the recommended checksum vendors should be using to protect the firmware? And a follow-up question is, if that specific or any other device that you have hit has that checksum, what would you done this? What would be, in short terms, your next step at that point?
Okay, so so if you have So this day and age, you should be using a cryptographically secure checksum and signing your firmware. So even if your hardware doesn't have like some sort of hardware security thing, you can write a bootloader that has some cryptographic secrets that don't get updated during the update process that can check the rest of it. So this, in this day and age, there's really no excuse for not using a full cryptographic checksum that you would traditionally do. So if it did have a full cryptographic checksum, the next thing that I would have done was to try to find some way to get the cryptographic secrets off of the device, or find some sort of race condition or whatever else. We have a bunch of different techniques we can use to break bootloaders. So we do that fairly often. Glitching attacks and stuff like that. Although most glitching attacks you can't do remotely. So usually at that point, I probably would have also gone down to pulling the stuff out of memory through some other means, and then finding a buffer overflow. And then instead of having a persistent rootkit on it, I would have just used the buffer overflow to install a rootkit. In these particular types of devices, one of the problems you have with secure bootloaders that don't have any hardware security is once I get code execution on it, I usually just write back to the bootloader and disable the cryptographic checks, and then I can upload unencrypted firmware. I do that quite a bit.
Awesome. Thank you.
Uh-huh.
Hey, just real quick, thank you, Jason. You make this sound, very easy to do. It also sounds kind of legacy-ish. So when is all this legacy stuff that my generation created just going to kind of go away, and what does the new world look like, and when is it going to get locked down? I mean, some of this is kind of like ridiculous, right?
Well, so when I first so it was 2002 when I was first handed my first control system and they said, go take this stuff over. And it was totally ugly and legacy. And I'm like, yeah, this isn't going to last very long. Unfortunately, I haven't had to evolve a lot since 2002, and now it's 2020. So 18 years later, we're super fast at this stuff. So the problem is that we never start. Years ago, then we really thought that this bad state would only last another 4 or 5 years, and then everybody would replace it out, and we'd have some legacy and less legacy every year and stuff. But the problem that we've had, especially in ICS, is just we never started. And so here I am 18 years later, and I'm using the exact same techniques and the same types of bugs to take over the stuff. So we never started replacing it. And replacing it's a hard problem. You've got all these interdependencies, you've got everything debugged. It's a lot of money to replace it. But if you never start, you never finish. So I think I've used up all of my time, and it's the next guy's turn. So I will turn you over to whoever the next guy is.